Great having you once again, my beloved scholars. Jam past question 2001, question number 32. In the circuit diagram below, the ammeter reads a current of 3 amps when R is 5 ohms and 6 amperes when R is 2 ohms. Determine the value of X. Our question is centered on circuit diagram, electric circuit diagram. Observe. Okay, looking at the diagram on the board, the question is saying, this is the ammeter, that anytime ammeter reads 3 amps, the R is 5 ohms. Okay, anytime we have 5 ohms resistor, our ammeter will read 3 amps. Then, if we have 2 ohms resistance, our ammeter will read 6 amperes. 6 amperes. Okay, I want you to observe something about this question. This question is in accordance to Ohm's law. Ohm's law that made us understand that the higher the resistance, the smaller the current. And the smaller the resistance, the higher the what? Current. When there is much resistance, then there will be less flow of charges. That's current. But when there is less resistance, there will be more flow of charges. That's current. Then observe and see. See, 5 ohm resistance, the current is 3 amps, 3 ampere. Then when the resistance lowers to 2 ohms, our current will increase to what? 6 amps. Then the question is said that we should find X. Okay, observe keenly. S is resistance. Then there is a trick I want you to observe in this question. There's something I want you to notice. The resistor changes with the reading of the ammeter, but something remains fixed in the question. There is something never changing, and those things are the EMF, the source of voltage, and the resistance of the resistor, called X. The resistor X remains there, and E, the EMF, also remains there. Okay, notice that from the question, it's only the reading of the ammeter and the resistor of a given resistance that is changing, but S and the EMF remains the same. And the best way to solve problem is to identify things that don't change. Okay, we can understand what I mean. Okay, to solve this, I'm very much aware that the variables are the current and the resistance. Then I will focus on the constants. My constants are the EMF and the resistor X, which is internal resistance. Yeah, this internal resistance of this cell, X. Then recall, to solve this, recall EMF is equal to current, open brackets, capital R plus small r. These are EMF formula, where I stands for current, capital R for external resistance, small r for internal resistance. However, this formula is for series connection. This formula is for series connection of resistors. You can see that in the brackets. In series connection, we're adding up the resistance to get effective resistance. But notice our diagram. Our diagram is coming in parallel connection. There is a junction here. And this junction will permit our current to divide. Therefore, this is parallel connection. Parallel. Then this formula, it will change a bit. Recall, to get the total resistance in parallel connection, we'll do this. 1 over RT is equal to 1 over R plus, okay, let me call this X. This R is for this one, the external resistance. Then this internal resistance, 1 over small r. Then the LCM becomes, LCM of capital R and small r is capital R times small r. Capital R times small r divided by capital R. I'll be having small letter r plus capital R, small r divided by small r. I'll be having capital R. This is 1 over RT, or total resistance. But recall, our concern is on total resistance. Then I'll reciprocate. I'll get the inverse. RT over 1 equal to, I'll also swap there. I'll also be having capital R, small r over small r plus capital R. This is my total resistance or effective resistance in parallel connection. Therefore, the EMF formula will change a bit because this one is parallel connection. This formula here is for series connection. Then, taking it to parallel connection, I'll be having EMF is equal to I, open bracket, capital R, small r over small r plus capital R. This is the formula that suits our diagram. That's the formula that suits our diagram. However, recall, our small r here is X. Our capital R is also capital R. Then also notice, since the EMF never changed in these experiments, in the first experiment, we had 5 ohms resistance and 3 amps or 3 ampere. In the second experiment, 5 ohms was taken away or replaced with 2 ohms resistance, and the reading changed towards 6 amperes of current. Then what do? Then we can now make a theory. And the theory is EMF in the first experiment is equal to EMF in the second experiment. That's true. The cell never changed. The cell remained the same. The EMF of the cell remained the same in both experiments. What was changing is the current and the resistance. Therefore, I can now say, since EMF is I, open bracket, everything here for parallel connection, I can now pick the first part. I in the first experiment, open bracket, the capital R in the first experiment, plus, okay, forgive me, multiply, follow the formula. Multiply the internal resistance, X, is constant all through, over the small r again, which is the internal resistance, X, plus capital resistance again, close it, equal to current in the second experiment, capital R in the second experiment, internal resistance over X again plus external resistance in the second experiment. We can now solve. Recall, the question says we should find the internal resistance X. Okay, we'll now push ahead. So in the first experiment, our current is 3 amps. 3, open brackets. Our capital R, 5 ohms. 5 times X over X plus 5. These are first experiments. In the second experiment, our current X, 6 amperes, 6, open bracket. Our external resistance in the second experiment, 2 ohms. 2, X is the same in both experiments, X plus 2, which is our external resistance. Recall, EMF in the first experiment is equal to EMF in the second experiment. We are targeting the unknown, which is what? X, the internal resistance. Then observe, 3 keys is safe, 1, 3 keys is 2. It's allowed, mathematically it's allowed. Then we are left with 5x over x plus 5 is equal to 2x over x plus 2. Okay, we'll continue. Then we have 5x over x plus 5 is equal to 2 times 2x, will be giving us 4x over x plus 2. Our target is to find x. At this point, we'll cross and multiply. Okay, we'll push ahead. Here we have 4x, open brackets, x plus 5 is equal to, here we have 5x, open bracket, x plus 2. Okay. So we'll push ahead. 4x times x, we'll be having 4x squared. Plus times plus. 4x times 5, we'll be having 20x. Is equal to 5x times x, we'll be having 5x squared. Plus times plus. 5x times 2, I'll be having 10x. Collection of like terms. Variables of the same kind will move together. Okay, we have x squared here, x squared there. So which one is a greater number? 5 is greater than 4x. I will send 4 the other way. And I'll get 10x towards 20x. So we start 20s, then 10x crossing equality sign becomes minus 10x equal to 5x squared. Then plus 4x squared going the other way becomes minus 4x squared. 20x minus 10x will give us 10x is equal to 5x squared minus 4x squared. Notice the same term. We'll be having just x squared. Just x squared. Notice we have x here and we have x squared there. So this x cancels one x. Finally, x is equal to 10 ohms. X is equal to 10 ohms. Finally, we've gotten our internal resistance, and that's 10 ohms. Going back to our options, we can see that the best option there is option C. Please stay tuned as we push ahead. Please do subscribe.